Hi, this video is going to recap what we were doing last night in our activity, and it's going to help you understand some ideas such as p-value, rejection region, and it's also going to help you understand the overall process of using a sample correlation to test what type of correlation exists in the entire population. And in this video, I'm going to be mostly doing demonstrations to try to explain these ideas. Here in Excel, I made up 3 different populations of 50 people to use for this demonstration. So over here in columns B and C, we have one population of 50 people. Over here we have another population of 50 people. And over here we have another population of 50 people. Let's look at this first population. Each row is a different person. So this row is person 1, this row is person 2, this row is person 3. And in each row, the left number is supposed to be the number of children that the person has, and the right number is supposed to be the number of hours that the person works per week. So the first person in this population has 1 child and works 5 hours per week. The second person in this population has 1 child and works 6 hours per week. If we move down, we can see that the 11th person in this population has 2 children and works 10 hours per week, and the 12th person has 2 children and works 11 hours per week. So that's what each of these numbers stand for. And let's try to find out what type of a correlation exists between number of children and hours of work inside this first population of 50 people. Well, if we look at the people who have 1 child, all of them work somewhere between 5 and 14 hours per week. I made it so that each person has a certain number between 5 and 14. So overall, all of these people with 1 child aren't working very much. And if you look at these 10 people who have 2 children, all of them are working somewhere between 10 and 19 hours per week, because I made the numbers 10 to 19. So overall, these 10 people with 2 children are working more than these 10 people with 1 child. So the people with 1 child work the least, and it looks like the people with 2 children work more. And down here we'll see that the people with 3 children are working even more, because if we look at these 10 people with 3 children, they're all working between 12 and 21 hours per week. And what about these 10 people who all have 4 children? They're all working between 15 and 24 hours per week. And these 10 people with 5 children are working between 20 and 29 hours per week. So overall, we can see that in this population, people with more children are usually working more hours per week, which means that this would be a positive correlation. And we can look at the correlation if we make a scatter plot. We just highlight these 2 columns, go to Insert, Scatter. Right here we see that these 10 people with 1 child down here are all working between 5 and 15 hours per week over here. These 10 people all have 2 children. You can see that down here. And they're all working between 10 and 20 hours per week. They all fall between 10 and 20. Remember, we have number of children down here on the bottom and hours of work on the side right here. These 10 people all have 3 children. and it looks like they're all working between, well, I said they're all working between 12 and 20 hours or 21 hours per week. If I put the mouse here, it shows me what the numbers are. If I put the mouse on one of the dots, it tells me what the two numbers are. See, this one is 3 and 20 at the top, and this one is 3, 12 at the bottom. These 10 people who have 4 children are all working between 14 and 24 hours per week. And these 10 people who have 5 children are all working the most. They're all working between 20 and 29 hours. So you can see that as the number of children goes up, the hours of work goes up along with it. So we have a positive correlation in this population. And it looks pretty strong. The dots are pretty close together. They're pretty close to following a straight line. So the correlation should be pretty strong. And it's you can see right here that the correlation coefficient for this population is a 0.8578, which is pretty close to +1, the highest possible positive correlation. Now let's look at the second population right here. This is another population of 50 people. These numbers over here are still the number of children, and these numbers are still the hours of work. Let's try to see what type of a correlation we have. Well, these 10 people who have 1 child are all working between 5 and 50 hours per week, because one person is working 5 hours, one person is working 10 hours, one person is working 15. I'm going up by 5s up to 50 hours per week. But if we look at the 10 people who have 2 children, when we look at their hours of work is still going from 5 up to 50 and up by 5s. So overall, these 10 people with 1 child are working the same amount as these 10 people with 2 children. And what about these 10 people with 3 children? They have the same hours per week, going from 5 up to 50. So we can see so far that the people with 1 child, the people with 2 children, and the people with 3 children are all working the same number of hours per week overall. And these people with 4 children, we're seeing the same numbers over here again for hours of work. And these 5 people with 5 children are working the same number of hours per week, between 5 and 50. Let's make a scatter plot and see what this looks like. Overall, it's a square because these 10 people with 1 child are all working between 5 and 50 hours per week. These 10 people with 2 children are working between 5 and 50 hours per week. The same thing over here. These people with 3 children are all working between 5 and 50 hours per week. So as the number of children goes up, people are working the same amount. As the number of children goes up, the hours of work isn't changing. So this square shape would be no correlation. There's no correlation between children and hours of work in this population. Now what about this last population, the third population? Well, if we look at these numbers over here, we can already see that it looks like the people with 1 child are working the most, because these 10 people with 1 child are all working between 20 and 29 hours per week. And if you look at the 10 people with 2 children, they're not working as much. they're all working between 15 and 24 hours per week. 15 to 24, that's a little bit less than what we had up here, because all of these numbers were all in the 20s. And these 10 people with 3 children, they're all working between 12 and 20 hours per week. So we're starting to see some numbers that are even lower than we've seen before. And these 10 people who have 4 children, all of them are working somewhere between 10 and 19 hours per week. So it definitely looks like as the number of children goes up, the hours of work is going down. So as what we're seeing is that as one thing goes up, the other thing is going down, which is a negative correlation. We can see that in this scatter plot. Right? The people with with one child are working the most. The people with 2 children are working less. The people with 3 children are working even less. The people with 4 children are working even less, and the people with 5 children are working the least. So this is a negative correlation. As the number of children goes up, the hours of work goes down. And it looks like a pretty strong negative correlation. Let's see what the correlation coefficient is. It's a negative 0.85, which is pretty close to negative 1, which is the strongest possible negative correlation. So we have, in this population, there's a strong positive correlation between children and hours of work. In this population, there's no correlation at all between children and hours of work. And in this third population, there's a pretty strong negative correlation between children and hours of work. So these are the 3 population correlation coefficients. And if we go to this slide right here, we can see that I pasted this population with a negative correlation up here. I pasted this population with no correlation right here. And I pasted this population with a positive correlation right here. And I'll put the correlation coefficients under each graph. So far I've been showing you that the symbol for a correlation is the letter R, but the letter R is actually only for a sample correlation coefficient, only if it's calculated with a sample. If it's a population correlation coefficient, meaning it's calculated with all population members, it's actually this Greek symbol, which is called rho, spelled like this, rho. That's for population correlation coefficient. So a population correlation coefficient calculated with all population members is rho. A sample correlation coefficient that's calculated with a sample is the letter R. Because actually, population values always have some type of Greek symbol. So in this population, rho was negative 0.85. Because I calculated the correlation with all 50 people, so it's the population correlation coefficient. If I didn't do it with all 50 people and I just selected 10 of them like this, and I calculated the correlation with just these 10 numbers, it would be a sample correlation coefficient because I didn't include all 50 people. But since I did include all 50 people in the formula, it's a population correlation, which is the symbol rho and not R. Over here, rho is 0. There's no correlation in this population. Over here, the correlation was the opposite. It was a positive 0.85. Now, I want to show you what type of samples. I want to talk about what type of correlations we would expect if we took a bunch of samples from this population right here with a negative correlation. Well, the sample correlation tends to fall close to the population correlation. So if the population correlation coefficient is negative 0.85, then most of the sample correlation coefficients will be somewhere near negative 0.85. Just like how the sample mean tends to be close to the population mean, the sample correlation coefficient tends to be close to the population correlation coefficient. But there's a few things we have to think about, though. That's really only true if the sampling is random. So if we randomly select a bunch of samples from this population and we calculate the correlation with each of the samples, most of the sample correlations should fall somewhere near the population correlation of negative 0.85. And it also depends on the sample size, because when the sample size is larger, the sample better estimates the population. So if we take a small sample, then the sample correlations will tend to be scattered further away from the population correlation, meaning they'll be scattered further below negative 0.85 and further above it out this way. But if it's a larger sample, then the sample correlations will be more closely packed around negative 0.85. The same thing is true over here. I said that if you randomly take a sample from a population and you calculate the correlation of inside the sample correlation coefficient, which measures the correlation in the sample, tends to be close to the population correlation coefficient. So if the population correlation coefficient is 0 right here, then most of the samples that come from this population will have a correlation coefficient somewhere near 0. And over here, if we randomly selected a bunch of samples from this population, most of those samples will have correlation coefficients near positive 0.85. Definitely some will be a little bit lower than this and some will be a little bit higher, but most of them would be near this number. And here's an analogy that we can use to help us understand this. We can imagine this number line right here as being the correlation coefficient number line that goes from negative 1 to plus 1, because we know that the correlation coefficient has to be somewhere between negative 1 and plus 1. And let's imagine that each of these populations is lined up with its correlation down here. So down here we have negative 0.85. This is lined up with 0, and this is lined up with its correlation of positive 0.85. Let's imagine each of these populations as being a helicopter that's hovering above its correlation coefficient. So since this population has a correlation coefficient of negative 0.85, it's hovering directly above the correlation coefficient of negative 0.85. So I said, we're imagining that this is a helicopter that's hovering above its correlation coefficient down here. Here we have another helicopter. This population is a helicopter that's hovering above its correlation of 0. And this population is a helicopter that's hovering above its correlation of positive 0.85. And when this population gives us a sample, we can imagine it as being like the helicopter dropping a package to the ground being this number line. And wherever the package falls is what the sample correlation coefficient turns out to be. So if this was a helicopter and it drops a package, we would imagine that the package should land somewhere near this number right here, near the population correlation. Because when you drop a package to the ground, it usually doesn't fall too far from where it came from. If a bunch of packages were dropped from this helicopter, some might land here, some might land out here, but overall they're going to probably land somewhere in this area near the population correlation. Now what about if this is a helicopter and it drops a bunch of samples to the ground? Well, if we imagine it as being like a helicopter dropping a bunch of packages, then most of those packages are going to land somewhere near 0, because the wind is going to carry it probably a little bit this way or a little bit this way, but overall most of those samples will be somewhere near 0. Now what if this population drops a bunch of packages to the ground? Meaning, what if it drops a bunch of samples? Well, most of them will be near this number right here. So this analogy is pretty much just a way to understand that when the population correlation equals a certain number, and you take a bunch of random samples from that population, those sample correlations tend to be close to the population correlation. So, we know that these are the 3 population correlations up here, and most of the samples from here, from this population, will be somewhere near this number. Most of the samples from this population will be somewhere near this number, and most of the samples from here will be somewhere near this number. And we can actually use Excel to show that this is true. I'm back in Excel. You notice how all of these red numbers have been added. These numbers might look like correlation coefficients, but they're actually not. These are numbers that Excel randomly generated in here. And the reason why I put these random numbers in here is because they'll let me randomly shuffle the population that we have here. This is how it works. Excel puts a bunch of random numbers in here, and then what I can do is highlight the 50 rows, like I did here, and then go to sort. There should be sort somewhere up here. Go to data, go to sort, and then sort by column D, which is the random numbers. Sort them from smallest to largest. And what it does is it rearranges them. It reshuffles the rows like this. So now these rows have all been randomized. And nothing has happened to the pairs because like this, each person still has the same left number and the same right number. But what it did is it just randomly shuffled the rows. So if we created the scatter plot again, it doesn't throw off the correlation because it's randomly shuffled the rows. Now, it's still the same correlation with a positive correlation of positive 0.85. Now let's sample this population. Let's take a sample of 10. And since I shuffled the rows, this will be considered a random sample of the population. A random sample of 10 out of 50 people. Let's see what this sample looks like if we create a scatter plot. It looks pretty positive, just like the population it came from. It's maybe not as strong of a positive as the entire population is. Let's see what the correlation coefficient is for this sample of 10. We'll go equals CORREL. Highlight these 10 numbers, the number of children for these 10 people. Put a comma. Highlight the hours worked per week by these 10 people. The sample correlation for those 10 people is positive 0.74, which is pretty close to the population correlation. The entire population had a correlation coefficient of 0.85, and the sample that came from this population had a correlation of 0.74. So it's a little bit lower. It's probably down here. It's probably our first sample, because if this is 0.85, 0.74 is probably down here, a little bit lower. Now let's sample this population again. We're going to have to reshuffle the numbers to get a new random sample. Go to sort, data, sort. So notice how it's not the same 10 people. It's a different sample of 10 people. There might be some people who were in our first sample who are also in our second sample, but it's not the same exact group of 10 people over again. There might be some overlap between the two samples, but it's not the same exact group of 10 people. So it looks pretty positive again, which makes sense because it came from a population with a positive correlation. Let's see what the correlation coefficient is. 0.8856, which is almost exactly the same as the population correlation. It's not exactly the same because the population correlation coefficient was 0.8578 and this is 0.8564. So 8578 and 8564 aren't exactly the same, but they're pretty close. So this one is maybe about right there. This sample correlation right here is just slightly below the population correlation. It's only very slightly below it. Remember, this was the correlation of 0.74. This one is basically 0.85. 0.8564. The only reason I put it a little bit below is because remember that the population is actually 0.8578. Now let's take a third sample. We have to reshuffle it again. We get a new group of 10 people. It should look pretty positive again, because it's coming from the population with a positive correlation. Yeah, it's pretty positive. Notice that how, even though all of the samples have been positive, all of the samples that we've taken don't look exactly the same. So the dots are always shifting around some, because different samples will give you different results. It wouldn't make sense for every sample to give us the exact same scatter plot over and over again. So let's see what this looks like. It's 0.84, which is again close to our population correlation coefficient of 0.85. It's probably right there. We'll do two more. It's a new group of 10 people. And now it looks like the correlation coefficient for these 10 people is actually 0.59. Excel calculated it automatically, but I'll show you how to do it again. This is our sample of 10 selected people. It's 0.59, so it's not quite as strong of a positive. So yeah, it's not as consistent looking. It's a weaker positive. So 0.59 is somewhere down here. So this one is actually underestimated the population correlation coefficient by quite a bit. Because here, R is 0.59. It's not a strong positive, it's only a medium positive. But a population with a strong positive correlation can give you a sample that only has a medium positive correlation, because the sample that you get depends on chance. It depends on the specific people that end up being selected. Now let's do one more. I'm reshuffling again. New group of 10 people. So Excel calculated this automatically. This sample of 10 people has a correlation of 0.9, which is a really strong positive. So yeah, this time the dots line up pretty well on a straight line. So 0.9 is up here somewhere. So 3 samples have underestimated the population correlation coefficient a little bit. 1 sample has underestimated it by quite a bit, and 1 sample has overestimated the population correlation coefficient. Remember that all 5 of these numbers are R's, because these are all the correlation coefficients of different samples. So there are 5 different R's. Now that we've already seen that when you take samples randomly from this population, the samples the sample correlation coefficients tend to fall near the population correlation coefficient. Just like how if a helicopter drops a package to the ground, the package tends to land somewhere near the helicopter it came from. But what if we were taking larger samples? What if instead of selecting 10 people, I was selecting samples of 20 people? If I selected 5 samples of 20 people instead of 5 samples of 10 people, these X's would have been even closer to 0.85. So they would have fallen in a narrower range around here. They probably wouldn't have been as spread out this far this way, or spread out as far out this way. For example, if we had used a larger sample size, we might have not gotten this outcome way down here, and this outcome would have probably been closer up here, and this one might have been closer down here. They would have probably been in a narrower range around the population correlation. Because with a larger sample size, the sample better estimates the population. Now let's take some samples from this population with no correlation. To do that, we have to shuffle these numbers. Remember that this population of 50 people right here is the population with no correlation, because these 50 people have a population correlation of 0. So now we're sorting by column H. A random sample of 10 people. And remember that these 10 people are coming from the population that has no correlation. Over here we have the population with a positive correlation, but now we've moved over to this population that has no correlation. we'll create a scatter plot with this sample of 10 people, and it looks pretty much like no correlation, just like the population it came from. Let's see what the R comes out to. That one wasn't correct, actually. It's not 0.9. It's negative 0.21. It's not that far away from the population correlation of 0. It's maybe down here, or probably negative 0.21 is probably down here, a little bit below 0 in the negative area. Let's take another sample from the population with no correlation. Oh wait, I'm reshuffling. It's pretty much no correlation again. And R is 0.12, which is a little bit above 0, probably up here. Here, the sample was down at negative 0.20. Here, it was up at positive 0.12. Let's take another sample. It's a little bit of a negative correlation, actually, just because of this dot down here. It might seem strange, but this one dot is actually making it a little bit of a negative correlation, because it's because over here at 1 we have these high dots that are really high, and down here at 4 we have this really low dot. So the difference between the dots at 1 and this dot at 4, the fact that it's dropping down like that is making it a little bit negative. So this sample is negative 0.33. It's a kind of a weak negative. Might be down here. This one was negative 0.21, and negative 0.33 is a little bit further to the left, closer to negative 1. Let's take 2 more samples from the no correlation population. Yeah, it's pretty much no correlation, and it's actually really weak. It's a negative 0.05, which is a very weak negative. It's basically 0. It's probably right about there. So we're taking one more sample. This time we got a 0.004, which is really close to 0. So there's really no correlation at all in here. I don't know where these other dots came from. That's strange. So this x would be really close to this x. I can move this other sample down here, and this one right here. So when you take a bunch of random samples from a population with no correlation, the sample correlation coefficients tend to be near zero. The sample usually falls pretty close to the population it came from. Just like how an apple usually doesn't fall too far from the tree. Let's take 5 samples from this population with a negative correlation. Remember that this population of 50 people is a population that has the negative correlation. So the sample does look like it has a negative correlation. These 10 people look like they're pretty much have a negative correlation. It's a negative 0.87. Which is really close to the population correlation. It's a little bit closer to -1 because the population correlation was negative 0.85. This is another sample. It looks pretty negative again. This sample has a correlation of negative 0.809. So it kind of pretty much rounds off to negative 0.8, which is probably down here. No, I'm sorry. It's a little bit out here, closer to 0. This sample looks negative again. Its correlation is negative 0.88, which is out here again. It's pretty much exactly the same as the other sample. So these two samples had pretty much the same number, I think. So I'm stacking them on top of each other. This one looks pretty negative again. And these 10 people have a negative 0.882. I'll do it again just to make sure. I might have forgotten to shuffle, so I'll do it again. I'll throw out that sample. Okay, so we got a negative 0.85. This looks like that. Negative 0.85 is a little bit closer to 0. It's a little bit to the right of the population correlation coefficient. It's probably right around the same area. Oh wait, I'm sorry. Negative 0.85 is the population correlation coefficient. So it actually the sample correlation coefficient came out to pretty much the same number as the population correlation coefficient. It's right there. We need one more. This sample came out to negative 0.88, which is the same correlation coefficient that these two samples had. So we're stacking another X right here. These three samples all had a correlation coefficient of negative 0.88. That's why they're all stacked on top of each other. This sample was negative 0.85. This one was about negative 0.80, I think. So overall, the sample correlation coefficient does tend to fall pretty close to the population correlation coefficient when you're doing random sampling, because these 5 samples all fell pretty close to this number right here. These 5 samples all fell pretty close to this number right here. These 5 samples all fell pretty close to this number right here, but by chance we got this one way out here. That happens sometimes. Now what we need to talk about is the null hypothesis and the alternative hypothesis. Whenever you're taking a sample from a population, and you're interested in whether there's a correlation in the population, there's 2 competing possibilities. Either there's no correlation in the population, like how it is here, or there is a correlation in the population, like it is here or here. And the null hypothesis, which is, they actually use this symbol for a null hypothesis, it's H0. And for an alternative hypothesis, the symbol is H1. So HO says there is no correlation in the population. H1 says that there is a correlation in the population. And if you look in a textbook or on a website, you'll often see these written out in symbols. I'll show you what I mean. You might see HO and H1. And you might also see that instead of writing no correlation in the population, they'll just write this symbol, rho, equals 0. Which basically means that the population correlation coefficient equals 0, like it does here. There's no correlation in the population. Each one says that the population correlation coefficient is not 0. It's some number other than 0. Because if the population correlation coefficient does not equal 0, then that means that there is some correlation in the population, either negative or positive. So this right here is basically saying no correlation over here, like it is here. And this right here is just saying that there is a correlation, like it says right here. This is just another way of saying this, and this is just another way of saying this. So when you're taking a sample from a population, and you actually don't know what the entire population looks like, you're trying to decide between two competing possibilities. There's the possibility that there's no correlation in the population, like this, or there's the possibility that there is a correlation in the population, like this, or like this. And later in this video, we'll get into how a person actually makes the decision about whether the population correlation coefficient is 0 or not 0. Before we can understand how to make the decision about the population, we have to talk more about what outcomes are likely to happen when the population has no correlation, and what outcomes are likely to happen when the population does have a correlation. Let's imagine that instead of just taking 5 samples of 10 people from this population with no correlation, we kept on taking many, many different samples of 10 people from this population with no correlation. If we kept on randomly selecting more and more samples of 10 people from this population, we would continue to get samples with correlations near 0. And the sample correlation coefficients would start to pile up like this. So we're imagining that each of these x's is the correlation coefficient of a different random sample of 10 people. So if I kept on selecting more and more random samples of 10 people and calculating the correlation of each sample, the samples would start to pile up like this. We'd continue to get a lot of samples with correlation coefficients near 0. And eventually, the sample correlation coefficients would start to follow a roughly normal distribution. For example, it might start to look something like this eventually. So if you keep on taking more and more random samples from a population with no correlation, and you calculate the correlation coefficient of each of your samples, the sample correlation coefficients eventually start to follow a roughly normal distribution like this, with a center at 0. And since samples that come from a population with no correlation follow this predictable shape that we're seeing right here, it's actually possible to predict what percent of the time the samples will fall in different areas on this number line down here. If you keep on taking more and more random samples of 10 people from a population with no correlation, and you keep calculating the correlation coefficient of each sample of 10 people, this is what will happen. Roughly 28.97% of the samples will end up landing in this area, green area right here. Between 0.2 and 1. So if you keep on randomly selecting more and more samples of 10 people from a population with no correlation, then roughly 28.97% of those samples will fall in this area right here. Roughly 28.97% of the samples will have a correlation coefficient between 0.2 and 1. And the same is true out here. Roughly 28.97% of the samples of 10 people that come from this population right here will fall between negative 0.2 and negative 1 in this green area. I'll make the green areas a little easier to see. So when you take more and more random samples of 10 people from a population with no correlation, and you calculate the correlation coefficient of each sample, about 28.97% of the samples will end up in this area, and roughly 28.97% of the samples will end up in this area. And since we know these percentages, it's possible to change these percentages to probabilities. I'll show you how we can do that. So this is actually 28.97% when 28.9% of samples from of 10 people from a population with no correlation will have, or I can just say will end up in this area. And the same thing is true out here. And if this is the case, then what that means is that each time we select a random sample of 10 people from a population with no correlation, that sample that we're selecting has a 28.97% chance of ending up in this area and a 28.97% chance of ending up in this area. Because if 28.9% of all of the samples end up in this area, then each individual sample has a 28.97% chance of landing in this area. The same thing is true out here. If 28.97% of all of the samples end up in this area, then that means that each individual sample has a 28.97% chance of ending up in this area. And when we talk about the chance of something happening, when we talk about a probability, we have to change it to a decimal. So instead of saying 28.97% chance, we would say each sample of 10, each random sample of 10 people from a population with no correlation has a 0.2897 probability of ending up in this area. So when I change the percent to a probability, I just move the decimal point 2 places to the left, and it changes the percent to a decimal. And the same thing is true out here. If 28.9% of the samples from this of 10 people from this population end up in this area, then each individual sample of 10 people coming from this population has a 0.2897 probability of ending up in this area. So each individual sample of 10 people that's randomly selected from a population with no correlation has a 0.2897 probability of ending up here and a 0.2897 probability of ending up here. If we add these two probabilities together, if we add 0.2897 and 0.2897, we would actually end up with a probability of a sample of 10 people from this population ending up here or here. Because if this is the probability of the sample ending up in this area, and this is the probability of the sample ending up in this area, then by adding the two probabilities, what you get is the probability of this happening or this happening, meaning the probability of the sample ending up out here or out here. So let's add those two probabilities. 0.2897 plus 0.2897 equals 0.5794. So there's a 0.5794 probability of the sample ending up in one of the two green areas. In other words, there's a 0.5794 probability that the sample won't end up in this middle area and will instead end up in one of the two green areas. And the total of these two probabilities that we just calculated is actually something called a p-value. The total of this probability and this probability is actually the p-value of these two correlations out here, 0.2 and negative 0.2. So here we would say p equals 0.5794. Out here, p equals 0.5794. The definition of the p-value is the probability, the p-value of an outcome is the probability of getting that outcome or a more extreme outcome when the null hypothesis is true. So in this case, what we mean by the null hypothesis being true is we just mean that the sample is coming from a population with no correlation. If the sample is coming from this population, then the null hypothesis is true because the population that the sample is coming from has no correlation inside of it. So, and let's think about what we mean here by more extreme outcome. If we look at this outcome right here of 0.2, all outcomes that are more extreme than 0.2 are just the outcomes that are further from 0 than 0.2. Basically meaning all of the correlations that are stronger than 0.2. When I say more extreme, you could just think stronger. So all of the correlations that are stronger than 0.2 are the correlations out this way toward +1, further from 0. And also, all of these correlations going from negative 0.2 out in this direction. So the outcomes that are more extreme than 0.2 are actually the outcomes in this green area and the outcomes in this green area. The two green areas make up all of the outcomes that are more extreme than 0.2 because all of these are further from 0 than 0.2, and all of these are also further from 0 than 0.2 is. So this p-value right here of 0.2 is what it means is that when the null hypothesis is true and a sample of 10 people is coming from this population, there's a 0.5794 probability that the sample will land at 0.2 or further from 0 out this way, or further from 0 out this way. So if I wanted to say that maybe in a different way, what I could say is that if we say that this negative 0.2 and this plus 0.2 are included in the green areas, then what this means is that, what this p-value means is that when a random sample of 10 people comes from this population with no correlation, there's a 0.5794 probability that the sample will land in one of the two green areas. When a random sample of 10 people comes from this population with no correlation, there's a 0.5794 probability that the sample won't land in this middle area and will instead land in one of the two green areas, out here or out here. Now, what about, well, now let's look at one other example. Let's, instead of looking at 0.2, let's look at 0.632. There's actually a reason why I'm choosing that number. But before we do that, I actually should redraw these samples, because I told you that you would expect 28.97% of them out here and 28.97% of them out here. So the random samples that are coming from this population would probably follow this type of a shape. It would actually be more spread out than what I made it look like, because I said 28.97% of the samples of 10 people from this population would end up out here, and 28.97% of them would end up out here. So when all of these random samples of 10 people are coming from this population, they're all falling down somewhere on this number line. A lot of them will fall in this area near zero, but actually 28.97% of them will end up somewhere out here, and 28.97% of them will end up somewhere out here in this area. And that means that each of these samples of 10 people has a 0.2897 probability of ending up out here, and a 0.2897 probability of ending up out here. And if you add the probability of this area and the probability of this area, the total of those two probabilities gives you the p-value of both of these boundaries, negative 0.2 and plus 2. Because, like I said, the p-value has to include the p-value of 0.2 includes everything at point 2 or more extreme, and everything out in this direction is more extreme than point 2 because it's further from 0, and everything out in this direction is more extreme than point 2, and this p-value of negative 0.2 includes everything that's more extreme than negative 0.2. So everything in this direction is more extreme, and everything in this direction is also more extreme. And I said that we would also look at the p-value of 0.632 and negative 0.632. So I'll erase this work down here. If you're wondering where these p-values came from, I actually got them from a website. I'll show you later how I got them. So right here, let's mark off negative 0.632. I'll erase some of this work that we've done earlier. It's hard for me to erase all of it. I'll do the best I can. Okay. So right out here, we have 0.632 positive correlation of 0.632 and out here we'll have a negative correlation of negative 0.632. And it turns out that when you keep taking more and more random samples of 10 people from a population with no correlation, that roughly 2.5% will end up in this area out here, this red area, going from 0.632 to 1. And roughly 2.5% of them will end up in this area out here, going from negative 0.632 to negative 1. So 2.5% and 2.5%. So 2.5% of random samples of 10 people from a population with no correlation will end up in this area. Same thing out here. 2.5% of random samples of 10 people from a population with no correlation will end up in this red area. And remember that if we want to change them to probabilities, we just have to move the decimal point 2 places to the left. So to 0.5%, you actually have to add a 0 in front and move this out here 2 digits to the left. And this actually changes to 0.025 as a decimal. So each individual random sample of 10 people has a 0.025 probability of landing in this area. Actually, what I mean is each individual random sample of 10 people from a population with no correlation has a 0.025 probability of landing in this area. And the same thing is true out here. Each individual random sample of 10 people from a population with no correlation has a 0.025 probability of landing in this area. So what this means is that if the random samples of 10 people that come from this population land in this red area 2.5% of the time and land in this red area 2.5% of the time, then altogether the random samples of 10 people coming from this population land in one of the 2 red areas, meaning here or here, 5% of the time. So that means that 95% of the time they land somewhere in this middle area between these 2 points right here, and 5% of the time they end up further out this way or further out this way in one of the 2 red areas. And now let's find the p-value of these 2 numbers, 0.632 and negative 0.632. I said that the p-value is just the total of the 2 probabilities. So when you add 0.025 plus 0.025, they equal 0.05. 0.05 plus 0.025 plus 0.025 is 0.05. So this p-value, this correlation is 0.05. This one is also 0.05. And the correlation that has a p-value of 0.05 is actually special because the correlation that has a p-value of 0.05 is the critical value. So a correlation that has a p-value of 0.05 is the critical value. So this one is a critical value, and this one is also a critical value. We have a negative critical value and a positive critical value. And we know that, I'm going to talk about why these are the critical values. We know that this area out here, starting at this critical value and going out here, is only reached 2.5% of the time. When the null hypothesis is true, meaning when the sample is coming from a population with no correlation. And we know that this area out here is also only reached 2.5% of the time. I said that the reason why these two areas aren't reached very often is because, in that situation, is because when the population that the sample is coming from has no correlation inside of it, when the sample is coming from this type of a population, then the sample tends to look like the population it came from. So if the population has a correlation coefficient of 0, the sample tends to have a correlation coefficient near 0. Like we saw earlier, most of the samples tend to pile up near 0. We saw earlier that our 5x's landed near 0. And it's unlikely for a sample coming from a population with no correlation to end up having a strong negative correlation and ending up out here in this area. In order for the sample to end up in this area, it would mean that you would have to take a sample from this. It would mean that a sample coming from this type of population, by chance, ended up with a strong negative correlation like this. And it's unlikely for a sample coming from this population to end up looking like that and having a strong negative correlation, because we saw earlier that when we take samples from this population, most of those samples look like they have pretty much no correlation. So, in other words, the only way that a sample coming from this population could end up with a correlation out here in this area is if somehow a sample from this population ended up looking like this, and that's not likely to happen. That's why samples from a population with no correlation only end up in here 2.5% of the time. They only end up in the strong negative area 2.5% of the time. But you have to remember that what this means is that if you do take a bunch of random samples of 10 people from this population, 2.5% of those samples will end up looking something like this. They will end up having a strong negative correlation, and they will end up out in this area. And also, we know that if you take a bunch of random samples of 10 people from this population, 2.5% of those samples will end up with correlations out here. What that means is that if you what means is that if you take a bunch of samples from this population randomly, 2.5% of those samples will end up looking something like this. They'll end up with strong positive correlations, and the correlation of the sample will be out here. But that only happens 2.5% of the time. So this area, this red area that starts at the critical value, it's only reached 2.5% of the time by samples coming from this type of a population, is called the negative rejection region. The negative rejection region includes all outcomes starting at the negative critical value and going to the left. And this area out here that's only reached 2.5% of the time by samples coming from this population is called the positive rejection region. The positive rejection region includes all outcomes starting at the positive critical value and going out toward the right. So why are these rejection regions important? Well, now we'll talk about why they're important and how they're actually used to make the decision about the population. So these two red areas are the rejection regions. The critical value is part of the rejection region, so I'll put it in red. In a real study, you're taking a sample from a population, and you actually don't know if the population has no correlation, a positive correlation, or a negative correlation. It's unknown. But you know that your sample is coming from some type of population. And what you want to do is try to make a decision about what type of population your sample came from. And there's two competing possibilities. Sample came from a population with no correlation is the null hypothesis. The alternative, H1, is the sample came from a population with a correlation. Another way of saying this is just, you could say that the null hypothesis is just the possibility that the population that you're studying has no correlation, and the alternative is the possibility that the population you're studying does have a correlation. That's just another way of saying the same thing. So these are two competing possibilities about this population that's being studied. And we don't know which one is true because we're taking a sample from this population, but we don't know if this population that we're sampling has no correlation or if it does have a correlation. And there's two competing possibilities. Either the null is true and it has no correlation, or the alternative is true and that there is a correlation in the population. To make the decision about this population, to decide between these possibilities, we have to look at where our sample ends up on this number line. We have to look at where the sample correlation coefficient falls. If it doesn't fall in one of the two rejection areas, meaning if it doesn't fall in one of these two red areas and it instead lands somewhere closer to 0 in this middle area between the critical values, we would not reject the null hypothesis, and we would continue to assume that the null is true. It's called failing to reject the null hypothesis. So the sample correlation coefficient lands between two critical values. And does not fall in one of the two rejection regions. You fail to reject the null hypothesis, and you continue to assume that the null is true, and that there is no correlation in the population being studied. And let's think about why that conclusion is made when the sample falls between the two critical values. The reason why is because if you look back at this slide right here, we can see that a sample coming from a population with no correlation could easily end up in the middle area between the two critical values, because a sample could easily fall here, 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 or anywhere between the two critical values. After all, we know that samples coming from a population with no correlation end up in the area between the two critical values 95% of the time. So let's make a table to help us understand what this means. We have the positive rejection region. We have the negative rejection region. And we have the non-rejection region, which is between the two critical values. So these are the different outcomes that we could have. Now let's think about different situations that are possible. Either the null is true, there's no correlation in the population. That's one situation that could be true. The population has a positive correlation. If that's the case, then the alternative is true, because If the population has some type of a correlation, the alternative is true. Or the population has a negative correlation, and that would also be the alternative being true, because the alternative just says that there's some type of a correlation in the population. So over here we have the different possibilities that could be true about the population, and over here we have the possible outcomes that might be found with our sample, because our sample could land in the non-rejection region between the critical values. It could land in the negative rejection region, or it could land in the positive rejection region. We know that when the null hypothesis is true, the sample is likely to end up somewhere in the non-rejection region, because when if the population has no correlation inside of it, if it's just the square shape that we saw earlier, then in that situation, the sample correlation is likely to fall somewhere near zero in this middle area. So if the null is true and the population has no correlation, the sample is likely to fall somewhere in the middle area in the non-rejection region, because that includes outcomes that are closer to zero. And if you do get an outcome in the middle area in the non-rejection region, you can't reject the null hypothesis, and the reason is because you have an outcome that would be likely to happen in the situation of the null being true. If the outcome that you have could easily happen when the null is true, you can't reject the null hypothesis. But what if your sample ends up in the negative rejection region down here, in this area that's only reached 2.5% of the time when the null is true? Well, if your outcome ends up in this area, you have an outcome that would be unlikely to happen when the null hypothesis is true, because if an outcome only lands out here 2.5% of the time when the null is true, then that means that a sample is unlikely to end up out here when the null is true. And since an outcome out here is unlikely to happen when the null is true, then if you do get an outcome out here, it leads you to reject the null hypothesis. Whenever you get an outcome that's unlikely to happen when the null is true, you reject the null hypothesis. So if your outcome ends up in this negative rejection region, you do have an outcome that's unlikely to happen when the null is true. So you do reject the null hypothesis. Now, if we've rejected the null, we've decided that the null hypothesis is not correct and that there's some type of a correlation in the population. But at that point, we want to decide which of these other two possibilities is true. We want to decide if we think the population has a positive correlation or if it has a negative correlation. Well, the sample ends up in the if our sample ends up in the negative rejection region, that's also unlikely to happen if the population has a positive correlation. Because if you get an outcome, if your sample ends up out here in this area close to -1 out here, then this sample right here is a strong negative. If you get a sample in the negative rejection region, then your sample looks something like this. It means you have a strong negative correlation out here. And this type of an outcome that you would find in the negative rejection region is unlikely to happen if it's it's unlikely to happen if the population has no correlation, and it's also unlikely to happen if the population has a positive correlation, because if the population is positive like this, it's unlikely for a sample from this population to end up being a strong negative. So this is also unlikely. So we can also reject the idea that the population has a positive correlation. But an outcome out here is actually likely to happen when the population has a negative correlation. Because if the population has a negative correlation, like this, and you take a sample of that population, you have a decent chance of getting a negative correlation in your sample, like this, that's strong enough to make it out here. If there's a fairly strong negative correlation in the population like this, you have a decent chance of getting a fairly strong negative correlation in your sample. So your sample is actually likely to end up in this negative rejection area. So that means that in this situation in which the population has a negative correlation, the sample is at least more likely to end up out here. So that would mean that if an outcome in the negative rejection region was unlikely to happen in this situation, then this is rejected. If it was unlikely to happen in this situation, that's also rejected. And if it's likely to happen in this situation, then we conclude that this appears to be true. So if your outcome is in the negative rejection region, you decide that the population has a negative correlation. So if your outcome ends up out here, you decide that the population has a negative correlation. That's the conclusion you reach when your sample ends up in the negative rejection region. Now what about if your sample ends up in the positive rejection region out here? Well, this area is also unlikely to be reached when the population has no correlation, because if the population has no correlation, then the sample is likely to fall in this middle area near 0 in the non-rejection region. It's unlikely to make it all the way out here into this strong positive area. So it's unlikely to be reached when the null is true, which means that if your outcome does end up out here, if your sample ends up out here, you reject the null. Whenever you get an outcome that's unlikely to happen when the null is true, the null is rejected. And you're also unlikely to get a sample in the positive rejection region if the population has a negative correlation, because if you get a sample in the positive rejection region, then that means that your sample has a strong positive correlation. Outcomes out here have strong positive correlations. So if I get a sample all the way in here, and my sample has a strong positive correlation, then you have to realize that a population with a negative correlation, like this, would be unlikely to give me a sample with a strong positive correlation like this. So a population with a negative correlation like this is unlikely to give me a sample that has such a strong positive correlation that my outcome ends up all the way out here. So the outcome is unlikely to land in the positive rejection region if the population has a negative correlation. So we reject the null hypothesis, and if our outcome ends up out here, we reject the null hypothesis, and we also reject this other possibility. But if the population has a positive correlation in it, if there's a positive correlation in the population up here, then our sample is likely to end up in this positive area out here in the positive rejection region. Or it's at least more likely to happen than it would be in the other two possibilities. So if our sample ends up out here in this positive rejection region, we decide that the population has a positive correlation, because out of these three possibilities that we have on the side right here, this possibility of a positive correlation is the possibility that would give us at least a decent chance of getting a sample in this area. These other two possibilities would be unlikely to give us a sample out here, which is why we reject this and reject this. So if you get an outcome that's unlikely to happen when the null hypothesis is true, you reject the null hypothesis and you pick the outcome. You pick one of these two outcomes, positive or negative, depending on which one is which one would be most likely to give you your outcome that you ended up finding. If you get an outcome in the non-rejection region that's likely to happen when the null is true, you don't reject the null hypothesis. So if you get an outcome that's likely to happen when the null is true, you don't reject the null. If you get an outcome that's unlikely to happen when the null is true, you do reject the null, and then you decide between one of the other two possibilities. So out here, we for outcomes out here, we decide that the population has a positive correlation. If we end up in the negative rejection region, we decide that the population has a negative correlation. If we end up in the positive rejection region, we decide that the population has a positive correlation. If we end up in the non-rejection region, in the middle, we decide to assume that the population has no correlation and that the null is true because we just don't have enough evidence to say that there's a correlation in the population. So now that we've covered the logic behind this hypothesis testing, I can now show you where the p-values and the critical values came from. Let's start with finding the p-value of 0.2. There's a p-value calculator right here. What we have to do is enter in the correlation that we're interested in, which is 0.2, and the sample size that we're using, which was 10 in this example, and we calculate. And it tells me that the p-value is 0.5795, which is, I think, what we ended up with. I think that's what I wrote down on here. About 0.795. What if we want the p-value of negative 0.2? It should come out the same. Right, it's the same number. Now, what about the critical values that we used? What about the 0.632 and the negative 0.632? I found out that those had p-values of 0.05 because to get these two p-values, we added this probability and this other probability. 0.632. Okay, so it's about 0.05. It rounds basically to 0.05, and then negative 0.632 would be the same. They both have the p-value of 0.05. That's why like I said, the two critical values both have to have the p-value of 0.05. That's because the critical value is the point it's at the point where the samples only go past these 2 points into the rejection regions 5% of the time when the null is true. That's where the p-value of 0.05 comes from. So if we want to review what we talked about with the p-values, when the null hypothesis is true and you're taking a sample of 10 people, when the population has no correlation and you're taking a sample of 10 people from that population, the sample ends up out in this area, starting at negative 0.2, going out 28.97% of the time. 28.97% of the time it ends up somewhere in this green area, starting at this dotted line, and 28.97% of the time it ends up somewhere in this area, starting at this dotted line. So, like I said, if you take a bunch of different samples of 10 people from a population with no correlation, 28.97% of them end up in this area going out from here, and 28.97% end up in this area starting here and going out. And when you combine these two, when you add the two decimals together, you get the p-value. And if you take a bunch of random samples of 10 people from a population with no correlation, 2.5% of them end up in this red area going out from here, and 2.5% of them end up in this red area going out from here. And when you add the two decimals together, 0.025 and 0.025, you get the p-value of these outcomes at the boundaries. And what would happen if we took a sample somewhere in the rejection region and found its p-value? Let's see what would happen in that case. Maybe we'll choose 0.8 right here and negative 0.8 out here. So this is 0.8. I'm just trying to give you a little bit more of an idea of how the p-value works. 0.8 and negative 0.8. Now you might guess that these outcomes out here would be especially unlikely to be reached when the null is true because they're so far from zero. And it turns out that this area, starting at 0.8, actually only has a point. It actually only has a 0.0027 chance of being reached when the null is true. And this area out here going out from negative 0.8. Sorry, I didn't mean to say 0.08, negative 0.8. So this also only has a 0.0027 chance of being reached when the null is true. So if this has a 0.0027 chance of being reached when the null is true, and this also has a 0.0027 chance of being reached when the null is true, then the p-value of 0.8 and negative 0.8 would be the total of those. .0027 plus 0.0027 equals 0.0054. That's the p-value. This outcome has a p-value of 0.0054 for 0.8, and this outcome of negative 0.8 also has a p-value of 0.0054. And I could have found this from the p-value. I found this from the p-value calculator. So